Okay, so among the few remaining topics we have left on alcohols, which again is part of chapter 7, we were getting started on the topic of oxidation of alcohols. And then I just want to say a few things about thiols, which are the sulfur analog of alcohols. And then I think that will basically be it. Then we'll be able to start chapter 9. So just getting a couple terms out there. O in square brackets and H in square brackets are simply abbreviations for oxidizing agents and reducing agents, respectively. They're just generic terms. But of course, in real life, we don't use generic oxidizing or reducing agents. We use actual compounds. And so the two oxidizing agents I'm going to expect you to know about are PCC, which stands for pyridinium chlorochromate. You can find the structure of that in your textbook, which is a mild oxidizing agent. Whereas Jones reagent, you can consider it to be either chromium 6 oxide or chromic acid. These two reagents are the same thing, by the way. Chromic acid is just the hydrate. You can see that if you add H2O to CrO3, you get H2CrO4. So these are the same reagent, just two different ways of writing the same thing. They're both called Jones reagent, and that's a much stronger oxidizing agent. And the reason you need to know that is sometimes it's going to matter which of those you use, sometimes not. That's going to depend on the alcohol. We already covered the easiest one on Friday, when we said that tertiary alcohols, and we've given examples of tertiary alcohols and we've defined that term, but any tertiary alcohol, you can treat it with either of those two oxidizing agents and nothing will happen. In order for an alcohol to be oxidized, that's one of the things we said on Friday, there needs to be at least one hydrogen on the carbon that has the OH group on it. And if there's not at least one hydrogen, game over. That alcohol cannot be oxidized. So by definition, since that's what tertiary alcohols are, tertiary alcohols cannot be oxidized. And it doesn't matter which of those reagents you try to use, whether PCC or Jones reagent, you're not going to get any reaction. Primary and secondary alcohols, though, can be oxidized. Maybe we'll do primary alcohols first. Primary alcohols can be oxidized twice or up to twice. If you treat a primary alcohol, you just wanted to see what's coming up. If you treat any primary alcohol, which is going to be an alcohol of this type, and we'll do some examples as well, with pyridinium chlorochromate, which remember is the milder of our two oxidizing agents, then you will get the corresponding aldehyde. By corresponding, I mean that it has the same number of carbon atoms. So that's going to be true for any primary alcohol. There are no exceptions. So for instance, if you took benzyl alcohol, and you treated it with PCC, they might mention the solvent in OWL. The preferred solvent for this is dichloromethane, CH2Cl2. That's not something that's not the hill I'm going to die on, whether or not you know that's the solvent. But just in case you see that sometimes in the textbook or on OWL, that's what they're talking about. These often reactions have a preferred solvent. In any case, the compound you'll get out at the end will be benzaldehyde. And the oxidation stops there with PCC. You don't get any further oxidation. As another example, if you took 1-pentanol, I'm going to push you a little bit and put the alcohol on the other side of the molecule because I want you understanding the concepts. I don't want you just memorizing pictures. But if you treat that with PCC, then you will get pentanal, which is a 5-carbon aldehyde. 1, 2, 3, 4, 5. 2, 3, 4, 5. Yep. So that's examples of primary alcohols being oxidized to the corresponding aldehydes. Again, corresponding meaning it will have the same number of carbons. be careful not to either add carbons or subtract carbons. You should have the same number of carbons in the product as in the starting material. So PCC is a mild oxidizing agent that will oxidize primary alcohols to aldehydes and no further. There's no further oxidation beyond that. Meanwhile, if you treat a primary alcohol with our stronger oxidizing agent, which is Jones reagent, and you can write Jones reagent, you can write H2CrO4, you can write CrO3. Those are all interchangeable terms. Doesn't matter which you write. But then you get further oxidation. I'm just going to write CrO3 here. I'll show you examples with it saying Jones reagent and examples with it saying H2CrO4 as well, so you can see what that looks like. In any case, then it oxidizes it beyond the aldehyde. The product you get is the corresponding carboxylic acid. Again, the carboxylic acid with the same number of carbons as the alcohol we started with. So we don't create any carbon atoms through this process. That would be kind of a problem. That would be a violation of the law of conservation of mass. So to give you some examples of that, if we took benzaldehyde, or sorry, benzyl alcohol, actually benzaldehyde too, but we'll get to that in chapter 9. Actually, it's very well timed. We'll get to that in just a short while. And you treated it with Jones reagent, you could write CrO3 or you could write H2CrO4. H2CrO4 and CrO3 are the same thing. H2CrO4 is just the hydrate of CrO3. Then you will get benzoic acid as the product. Whereas if we took 1-pentanol, and treated it with Jones reagent, you can even just write Jones. That's fine. Then you will get the corresponding carboxylic acid. You will get pentanoic acid. 1, 2, 3, 4, 5. So it will have the same number of carbons. So bottom line in terms of what you need to know. Tertiary alcohols cannot be oxidized. Does not matter which oxidizing agent you use. Primary alcohols can be oxidized up to twice. If you treat a primary alcohol with pyridinium chlorochromate, which is our mild oxidizing agent, you'll get the corresponding aldehyde. If you treat a primary alcohol with Jones reagent, whether that's written CrO3 or H2CrO4, or just Jones reagent, doesn't really matter, then you will get the corresponding carboxylic acid. And actually, one of the things we'll see when we get to chapter 9, again, it's just lucky timing here. It turns out that if you take an aldehyde and treat it with Jones reagent, you will get the carboxylic acid as well. So we'll cover that officially in chapter 9, but I might as well mention that now as well. Good. So I think that's all I really need to say about that. Questions on oxidation of primary alcohols, or I could do some more examples. Would that help? Okay, we'll do more examples. Let's do, what would be a primary alcohol? Maybe one that's a little bit less boring than 1-pentanol. That's a primary alcohol. If you treat that with PCC in dichloromethane solvent, then you will get the corresponding aldehyde, which would look like this. However, if you take the same alcohol and you treat it with Jones reagent, CrO3, H2CrO4, whichever you want to write, then you will get the carboxylic acid. The oxygens, by the way, come from the reagents themselves. So, right. And I guess technically you also get molecules of H2 out of this. Any extra oxygens are going to be provided by the reagents themselves, especially by, well, you can see there's oxygen in Jones reagent. So that's where the extra oxygen comes for the carboxylic acid, for example. That comes from the inorganic compound. So that's basically it. Of course, we're not doing mechanisms or any such thing. I don't think the mechanisms of those reactions even are known. Question, yes? Yeah. The question is about, tell me if I'm interpreting you right. You're saying about how primary alcohols can be oxidized twice because it can act upon the aldehyde. I think that's kind of, am I understanding right? Yeah, that's right. Another way of thinking about it, remember we said that in order to be oxidized, the carbon has to have at least one hydrogen on it, which in the case of an aldehyde, it still does. So that's why it cannot be oxidized further. It all fits in the same rule, essentially. Do you mean, would you want to show the primary alcohol becoming the aldehyde and then becoming the carboxylic acid? It becomes an aldehyde and stops. Yep. Right, but notice Jones reagent will oxidize the primary alcohol also. It actually is two oxidations. It actually oxidizes the alcohol to the aldehyde and then keeps going, whereas PCC stops at the aldehyde because it's a milder oxidizing agent. It's a fine point. I would say you will know whether you need to show the aldehyde also depending on how the question's phrased. That's right, and you would know if you need to show it based on how the question is phrased. If it says to show the intermediate, then you show the intermediate. Normally we don't, but that is true. There is an aldehyde intermediate that then oxidizes further. But for PCC, it stops. Yep, yeah, good point. Other questions then? Well, having weathered that, I think you're going to be just fine with secondary alcohols. That's somewhat simpler. Secondary alcohols are oxidized to a ketone regardless of the oxidizing agent. Regardless of the oxidizing agent used. So I would say if you have an alcohol of this type, that's a secondary alcohol. We'll do examples too. There's a secondary alcohol. You can treat this with either PCC or Jones reagent. It does not matter which you use, and you will get the corresponding ketone. And it stops there because ketones cannot be oxidized any further. Remember our rule, we're looking for a hydrogen on that carbon, and there are none. So that's how you know you're done. Ketones cannot be oxidized further, just like tertiary alcohols cannot be oxidized further. They don't fall into our rule of needing at least one hydrogen on that carbon in question. So it does not matter whether you use PCC or Jones reagent. The product's going to be a ketone. And I have some examples of that as well. Let's say we used 2-pentanol, which now we know how to name alcohols. You could take your pick. If you used PCC, for instance, you would get 2-pentanone as your product. And there, by the way, is a little example of how to name ketones. Pretty straightforward. That's why I said if you know how to name alkanes, you know at least 85–90% of what you need to know to name anything else. Everything else just falls right in line. Meanwhile, if you use Jones reagent instead of PCC, you'd also get the same compound. So secondary alcohols can only be oxidized once, and the product will always, without exception, be a ketone. There are no exceptions. The product of oxidizing a secondary alcohol is always a ketone. No exceptions. Let's say you took, just to give another example, cyclopentanol. You could treat this with Jones reagent, write that however you like, CrO3, H2CrO4, same difference. And the product will be cyclopentanone. Let's see if I can make up another secondary alcohol. I just want to be sure I do enough examples. Let's go crazy. Let's do this one. So that's a secondary alcohol. That falls right in with our definition of secondary alcohols. By the way, notice for all of these, you have that all-important hydrogen attached to that carbon. That's what tells us that it can be oxidized again. That's the hydrogen that's going to be removed in this case during the oxidation reaction. And you can write Jones reagent, or you can write either of the formulas that's a stand-in for Jones reagent, and you will get acetophenone as your product. And that's basically it. Like I said, we're not doing mechanisms or anything like that. And I'm almost positive in this case, the mechanism isn't even really known. These reactions have been known for a very long time, but I think exactly how they work is still somewhat of a mystery. I'll do another example. If I can think of a sufficiently interesting one. There's a secondary alcohol. You can treat that with PCC, you can treat that with Jones reagent, and you just turn the alcohol into a ketone. You essentially lose a molecule of H2, and that gets absorbed by the inorganic reagent and taken out of the mixture. And that's basically it. So secondary alcohols are pretty straightforward. They're oxidized to ketones, and that's it. That's the only possible oxidation product in any conceivable universe, really. Tertiary alcohols are also straightforward. Game over. No oxidation possible. Primary alcohols are the ones with two options. Primary alcohols are oxidized by PCC, which is our mild oxidizing agent, to an aldehyde, and then they stop. Whereas if you treat a primary alcohol with Jones reagent, you get the corresponding carboxylic acid as the product. As you pointed out, first through the aldehyde, but then that gets oxidized further to the carboxylic acid. And those will also be without exception. You don't need to worry about trick questions or exceptions. There are no exceptions. I don't think even OWL can come up with a trick question about that. Though I'm sure they'll try. Good, let me make sure we still need to cover, well, I should say something about alcohols with more than one hydroxyl group also. Makes sense. Any questions on oxidation of alcohols? You mean I did it again? That was so clear that no questions are even possible. I wish I were such a good teacher. Okay, well, there's a section here about alcohols with more than one OH group, which is pretty timely because we're going to have a chapter in carbohydrates coming up pretty soon. And carbohydrates are loaded with OH groups. So it's not uncommon to have more than one OH group. You already know about glycerol. One, two, three propane triol. That we covered that in, this also counts as exam review because we covered that in the chapter on lipids. So that's certainly a compound that exists, and these things are quite stable. A somewhat similar compound that is not glycerol is 1,2-ethane diol, which we usually call ethylene glycol. Unlike glycerol, ethylene glycol is pretty toxic. And you find ethylene glycol in antifreeze, which, I mean, that was a big consideration when I lived in Minnesota for 16 years. But now that I'm down where it's warm, I guess you still need something. The nice thing about ethylene glycol is it's a liquid over a very, very wide range. So even at extremes of temperature, the coolant remains in the liquid phase, which is kind of what you need in order for it to work well. But there are lots and lots of examples of compounds with more than one OH group. It's certainly something that's allowed, and compounds like that are very stable in general. As for thiols, the thiol functional group thiol functional group is just SH. And even though we're not doing the chapter on ethers, let's remember that a thioether is also called a sulfide. Essentially R1SR2. So it's a compound of that type. So thiols are the sulfur analog of alcohols. Sulfides are the sulfur analog of ethers. And they have properties somewhat similar, except that we already mentioned how thiols are significantly more acidic than alcohols. And we also went over why. This also counts as exam review. We said that it's because the sulfur atom is so much bigger than the oxygen atom. And so when you make the conjugate base, you guys remember how to make the conjugate base by removing a hydrogen, right? That's a thiolate ion. That's the conjugate base of a thiol. Well, that minus charge is now distributed over a much larger surface area than for the oxygen atom. And so it's comparatively a more stable situation. There's more space for the negative charge to spread out on. Remember, like charges repel. And so anything you can do to spread out that minus charge, that's something we also covered in chapter 17. And is an idea we'll hit on in other chapters as well. But the more that you can do that, the more stable the conjugate base is, and anything you can do to stabilize the conjugate base makes the acid stronger. And the effect is pretty dramatic. Thiols are, other things being equal, generally at least 100,000 times more acidic than alcohols. Again, other things being equal. But other than that, there are many similarities between thiols and alcohols and between sulfides and ethers. One big difference is both thiols and sulfides stink to high heaven. And anyone who's ever smelled a skunk knows about that, because there are both thiols and sulfides in skunk spray. You might also, it just all depends if you've been in a situation, I kind of hope not, because it's kind of a dangerous situation. But if you've ever been in a situation where you've, quote, smelled gas or smelled natural gas, natural gas is actually odorless. But as you can imagine, that's a real safety problem. We need to know when there's a gas leak because we don't want the whole thing explodiating, right? And in order to avoid explodiations, what they do is they put a small amount, a very small amount, like a fraction of a percent of a thiol into the natural gas. And that way, you're not going to miss that odor when there's a natural gas leak. So if you've ever, quote, smelled gas, you're not really smelling the natural gas. You're smelling the additive. And you've noticed how that improves the safety considerably, because then you know, hey, there's a gas leak. We need to do something. Yes. Mm-hmm. Mm-hmm. Yeah, good question. The question was, if there's a molecule with multiple OH groups and you oxidized it, yes, you would wind up oxidizing all of them. And if any or all of the alcohols are primary alcohols, then we have choices. We can use either of those two oxidizing agents. If any or all of them are secondary alcohols, then there's only one possibility. You get the ketone. But yes, absolutely, you would oxidize all of them. Yep, good question. One other quick thing about, I lied, two other quick things about thiols. Thiols are really easy to make. You make them from alkyl halides with the hydrosulfide ion, NaSH. And we didn't cover chapter 6, but this is what's called an SN2 reaction. Like I said, I don't expect you to know that it's called that. We haven't covered that chapter. However, the mechanism is dirt simple. It's so easy, I don't mind showing it to you. There's your SH minus ion. It simply attacks, as we say, the carbon that bears the halogen. It doesn't have to be bromine. Chlorine or iodine are also fine. So, and you get the corresponding thiol. Plus, in this case, you would also get sodium bromide. So it's very straightforward to make thiols. That reaction works very well. Another reaction of thiols that's interesting and might have some relevance when we get to our chapter on proteins and polypeptides is that you can actually oxidize thiols in a way that you cannot oxidize alcohols. But there are oxidizing agents, both biological and otherwise, that will take two thiol molecules and generate what's called a disulfide. Let me get all these stray marks out of the way. So that's a reaction that's special for thiols. You can't do that with alcohols, at least not in the same way. So the reason that's relevant to polypeptides is you might be aware that one of the amino acids, the one called cysteine, has a thiol functional group. And so what can happen is you might have a protein with 10,000 amino acids in it. And you can have a cysteine residue with its SH group over here, and another cysteine residue with its SH group in a totally different part of the molecule. And they can come together and form that disulfide linkage. And one area in which that gets applied, not really sure how many people nowadays still get a perm. I just wish I had enough hair that I could get a perm if I wanted to, but unfortunately that's no longer possible. But when you get your hair styled like that, it effectively breaks and then resets, reforms all of the disulfide bridges from cysteine residues in the proteins in your hair. And it sets them in a certain way so that it will stay that way for a long time. So that's just one example. There's probably better applications than that. But don't know the last time I've ever seen anyone get a perm. When I was growing up, it was a lot more, although I did have a colleague at my previous school who would get his hair permed. I was always jealous of him. I was just like, wish I could do that if I wanted to, even though I maybe don't, but I wish I could if I wanted to. Okay, so actually with that, I think we're done with chapter 7. So certainly if there are any questions, feel free, but I'll just say that's it for exam 3 material. We're going to start chapter 9, but that will not be in Friday's exam. Yes? Yeah, this is HS minus ion, and it comes from, it's the same thing as this. NaSH is Na plus SH minus. So it basically is this. The sodium ion doesn't do anything. It's just a spectator ion. So like I said, we technically didn't do that mechanism or that chapter with that mechanism in it, but it's actually one I don't mind showing you guys because it's a fairly straightforward mechanism. It has just one step. Something with 10 steps, that'd be a bit much, but one step I think we can do. Yeah, so thiols are pretty easy to make. Good, other questions then? All right, well, so like I said, we are done with material for Friday's exam, for exam number 3. The rest of the material from today and the material on Wednesday will be in exam number 4, which is right after Thanksgiving, which I'm panicking about when I'm actually going to get that copied, let alone written. But as with so many things, that is not your problem. That's my problem, and we'll solve it. Wow, 23 people in chat. I'm glad they at least come and chat. Good, so I would say a long-standing traditional part of the organic chemistry 2 curriculum in those where you get, in those cases where you get 2 semesters of organic chemistry is on carbonyl chemistry. And we're going to have a lot to say about the carbonyl group in this chapter, as well as in a couple of other chapters. So just in case you're curious, we've basically, in a sense, moved on from organic 1 to organic 2. And so some of your colleagues, if you will, that are in my Chem 228 classes are covering carbonyl chemistry right now. And we'll cover some of it. Of course, we're not going to go into nearly as much detail, but we'll cover some of it. And I would say this whole chapter is about nucleophilic addition reactions to ketones and aldehydes. And it's going to be a good background for when we get to our chapter in carbohydrates, because there's a lot of that kind of chemistry that goes on there as well. So we're going to be applying that. to biologically relevant molecules in the foreseeable future, let's say. I will have a lot more to say also about the carbonyl group in general, probably on Wednesday, because that's in section 9.5, and I want to save that for Wednesday. But I just want to walk us through the first few sections of chapter 9, which are mainly on naming aldehydes and ketones, of course, the structure of aldehydes and ketones. And I also want to say a few quick things about hydration of aldehydes and ketones, which it's in your class notes, but I believe that's in section 9.8. So sections 1 through 4 and section 8 of chapter 9 are the ones that are not mentioned in the syllabus, but they are mentioned in the chapter 9 class notes. And so those were the ones I meant in my email when I said that there's some sections that the syllabus doesn't mention, but it does make it clear in the chapter 9 class notes that you'll be responsible for them. Again, not for Friday, for exam number 4, when we get back from Thanksgiving. Oh, Thanksgiving seems so far away, which is good. That gives me time to solve all those problems. Be that as it may, I'm going to assume for this chapter that you're familiar with all your functional groups, that you know what an aldehyde is, that you know what a ketone is. We just saw some examples of those compounds as well, so it's fairly well timed. In terms of naming ketones and aldehydes, there are some small aldehydes and ketones that are prepared industrially by the ton every single day. The 1-carbon aldehyde is called formaldehyde. You're probably familiar with formaldehyde. You're probably familiar with the smell of formaldehyde. If you did any dissections in high school biology or even in college biology, well, then you're familiar with formaldehyde, which is used to preserve biological specimens. And I'll just say also, I might have mentioned this earlier when we talked about functional groups. Almost all aldehydes smell very disagreeable, smell something like that. The one notable exception being benzaldehyde, which you know what benzaldehyde is. That's one of the compounds you would learn about in chapter 4. And I couldn't tell you why this is, but for some reason, benzaldehyde smells very pleasant. People disagree on what exactly it is they're smelling. Some people say it smells like almonds. Some people say it smells like maraschino cherries. But pretty much everyone agrees it smells very pleasant. I have no idea why. It's just mysterious how our smell receptors work. The next larger aldehyde after formaldehyde is called acetaldehyde. And that makes sense. Similarly, the 2 smallest carboxylic acids are formic acid and acetic acid. So they use the same roots. The smallest possible ketone has 3 carbons. You have to have at least 3 carbons to have a ketone. And that compound is called acetone. You could call it 2-propanone. No one really does, though. It's not wrong. It's just no one really calls it that. Everyone calls it acetone. And you'll find acetone in all sorts of industrial and commercial products. You'll find some acetone in nail polish remover. You find it in anything like turpentine or paint thinner will have some acetone in it. So it shows up quite a bit. What about aldehydes and ketones that we name using the standard IUPAC naming, like we learned back when we were learning how to name alkanes? That's usually fairly straightforward as well. So if you had a compound like this, that would be called 3-pentanone. Right? You would start numbering 1, 2, 3. Doesn't matter which side you start numbering for, you'll get to 3. So you use pentane as the root, and you use the -one ending to show that you've got a ketone. So they're usually fairly straightforward to name. Or this compound. We would call that cyclohexane. Probably you would have guessed that. As for aldehydes, they usually take the al ending, Al. So if you had something like this, we would start numbering carbon 1 at the aldehyde carbon. The aldehyde carbon always will be on the end by definition. Otherwise, it wouldn't be an aldehyde. And so, 5, 6, there we go. There's 6 carbons total in the chain with a methyl group in carbon 5. So we would call that 5-methyl hexane al. Not all for alcohols, but al for aldehydes. So that's how we name them when there are longer chains. But these few compounds here, you're going to run into names like that pretty often. They're just very commonly referenced compounds. And yes, it is not wrong to call formaldehyde methanal and to call acetaldehyde ethanal, but no one really does. We use the names formaldehyde and acetaldehyde for those. We already talked about what formaldehyde is used for. So those are the basics of naming aldehydes and ketones. All of these compounds are made industrially, especially the smallest ones. Those are made by tons and tons every single day and are then used to make other things. They're very common synthetic starting materials. Another reaction that you already know that will provide a ketone, we learned in chapter 4, which was on aromatic compounds. In fact, in section 4.9. So if you've forgotten about this reaction, please review it. You will need to know it in order to understand the material in chapter 9. But there we said that you could take benzene and treat it with any acid chloride, like let us say that acid chloride, as well as either iron 3 chloride or aluminum chloride. And the compound that you will get out of it will be an aromatic ketone. Let me be careful to draw the right one. 1, 2, 3, 4, 1, 2, 3, 4. Yep, that's the compound that you'll get. And you'll also technically get a molecule of HCl out of it if you want to have a balanced equation. That's an inorganic side product. The aluminum chloride is, of course, just a catalyst. So that's neither consumed nor generated over the course of the reaction. You just need a little bit, maybe 1/10 of a mole equivalent in order to get the reaction going. So the reason we're mentioning this is because the chapter is on aldehydes and ketones to an extent. So that's why it makes sense to go back and make connections to material in earlier chapters, because this is a method for making ketones that we already know. And it's very effective for making aromatic ketones like this one. Yes, we have 10 minutes left. I'm not quite sure we'll have too much time for review. I'll try to leave a little bit. Maybe we'll at least say some things about chapter 13. But I want to talk a little bit about oxidation of carbonyl compounds, since we actually just went over that. So it's actually pretty well timed. And I also want to say a few things on hydration of aldehydes and ketones, just a little bit, since that's in section 8, which is in your class notes. And that way will be, I might even leave that for Wednesday, to be honest. That can probably wait till Wednesday. But one of the features of the reactivity of aldehydes is they're actually not all that stable. They tend to oxidize just in air. So if you treat an aldehyde with half a mole equivalent of oxygen, then you will get, slowly but surely, the corresponding carboxylic acid. So aldehydes are pretty easy to oxidize. We also know that you can get from an aldehyde to a carboxylic acid using our new friend, Jones reagent. CrO3 or H2CrO4. So that's another thing we now know. But aldehydes can be oxidized to the corresponding carboxylic acid, either quickly with Jones reagent, that's going to be when we want to do it on purpose, or even if we're trying not to oxidize the aldehyde, over time, gradually, they will oxidize just from the oxygen and air, and you will get some of the carboxylic acid. So they're not the most stable functional group in all the world. Yeah, you know what? Let's leave addition of water. I think that will rather than my shoehorning it in now, I think it will make more sense in Wednesday's lecture. So that's probably enough from chapter 9. Let's do some review of chapter 13. But before we do that, any questions on any of this? So, sorry. So remember, I don't have any sample questions from chapter 13 because you're the first class that I'm trying to do chapter 13 in. But if you want a study guide for chapter 13, you can find it in a couple places. You can find it at the end of chapter 13 in your textbook, where it lists every single topic in the whole chapter. They've got pretty good chapter summaries in your textbook. And I also believe I listed, if not all, certainly almost all of the topics in chapter 13 in the chapter 13 class notes, which I did make available before the lecture on chapter 13. Let me actually turn to those. Let's see. Wow, that's way back. Chapter 11. There's chapter 13. So one of the heterocycles that you'll need to know about and that we covered in chapter 13 is pyridine. And pyridine looks an awful lot like benzene. It's an aromatic compound like benzene, pyridine, Pyridine, pyridine. And as such, it has some similarities to benzene. Certainly, it's a planar molecule like benzene. Some differences between pyridine and benzene. Pyridine is certainly a good deal more basic than benzene because it has that amine nitrogen in it. So pyridine is able to act as a base and abstract a proton from a sufficiently strong acid. Pyridine is also very water soluble, which benzene is not. That's because the nitrogen atom is able to act as a hydrogen bond acceptor for the same exact reason as the nitrogen bases in nucleic acids. So you're getting some chapter 18, or is it 15? 18 review as well, because we talked about that in chapter 18. Pyridine also is able to undergo electrophilic aromatic substitution reactions of the type that we talked about in chapter 4, but it's much more difficult. And I would say the main reason it's so much more difficult is because of, obviously, that nitrogen atom is the only difference. So it has to have something to do with the nitrogen atom. And it's because nitrogen is pretty electronegative. It holds the pi bonding electrons in more tightly. And so it makes it much, much harder to react. You can do it, but it makes it much harder to react pyridine than benzene with all of those reagents we talked about in chapter 4. So again, if you've forgotten about those, it's not a bad time to review them. It's certainly going to be fair game for the final exam. We also talked about quinoline. Quinoline is kind of like, oh, what's it called? Come on, Jack. Oh, that's going to bother me. Why cannot I think what that's called? It's in mothballs. Naphthalene. That's right, naphthalene. Because naphthalene is just 2 fused benzene rings. It's one of our polycyclic aromatic hydrocarbons. And there's another one that looks quite a bit like it, called isoquinoline. These were also, whoops, not quinol, quinoline. These are a little bit harder to get all of the double bonds in. I find that one a little bit more confusing. But isoquinoline just has the nitrogen in the other place. They're both kind of like naphthalene, except of course a lot more basic than naphthalene because they have that nitrogen. Both of them, of course, have that lone pair on nitrogen. We also covered let's see, we covered the various diazines, the most important of which I would say is pyrimidine. Pyrimidine. because that compound is analogous to the pyrimidine bases that we find in DNA and RNA. There's also two other diazines. You can also have the two nitrogens right next to each other. You can also have them in the 1 and 4 positions relative to each other. But I would say of the 3 diazines, that's the one that we're going to use the most. In fact, we did use it in chapter 18. So that's a fairly important one. We also talked about furan and thiophene. And pyrrole. This is NH over here. These 3 compounds are aromatic like benzene. And we drew the resonance forms to show why that is. They have a delocalized pi electron system, just like benzene does. So those are also very important heterocycles. You run into them a lot. Let's see, I at least want to get through chapter 13 if I can. We also talked about how these 3 compounds can also undergo electrophilic aromatic substitution, just like benzene, except they're actually a good deal more reactive than benzene. And we discussed the reasons for that. That has to do, again, with how all 3 of those are resonance stabilized species. You wind up having partial minus charges on the carbon atoms, so they react very readily. I guess we also did oxazole, imidazole, and thiazole. The imidazole ring system NH, yes. Imidazole. The 3 azoles, these are called. Imidazole, oxazole would have an oxygen over here, not OH, just oxygen, and thiazole would have a sulfur there. That's something we also talked about, is how you can get clues about which elements are in the heterocycle from the name. Doesn't work 100% of the time, but it allows for a pretty good educated guess. But the imidazole system you will find in the amino acid histidine. So we'll run into that. And as far as that goes, there's also the indole ring system. This is probably a good one to end on since I'm pretty much out of time. Indole is another heterocycle. You'll find that in the amino acid tryptophan. So with that, I'm actually out of time. So I need to let you guys get going. Do I mean chapter 15? Chapter 15 I thought was lipids. Double check me on that. But I think chapter 18 is nucleic acids and chapter 15 is lipids. Both are on exam 3 anyway. But I believe that's the case. Good. So have a good day and I will see you all on Wednesday.